All right, hey everybody. So today I'm super excited to be able to introduce to you the second fundamental form. Right? We've already seen the first fundamental form, which gave us a way to make measurements on the tangent space at a given point of a surface. And then we could do things like measure the length of vectors in that tangent space. We could go on to compute things like lengths and areas on our surface and so on. The second fundamental form works a little differently. It will be a measure of how our surface is curving in space. And it will do that by measuring how much our surface's normal vector moves in a given direction. But let's not get ahead of ourselves. We're going to take as a setup a surface that's at least C2, so we can take at least two derivatives of the parameterization. It's parameterized by a capital X. And then we're going to say that the second fundamental form is going to be a function. At each point, it will be a function from the tangent space of the function into the real numbers. And it's going to be given by the expression, we're going to use the Roman numeral 2. So 2 sub p of a vector v that's lying in that tangent space is going to be measured as negative differential of v dotted with v. And as a reminder, because we are in this tangent space, that dot product is the R3 dot product, but within the tangent space itself, it can be thought of as the first fundamental form. So this is really negative first fundamental form of p of, dnp of v dotted with v. All right, so that's an equivalent way to write this. So what we're doing here, right, is we are in a certain sense measuring how much our normal vector, capital N, changes when we move away from the point P in the direction given by V. And we'll see going forward why this is the case, right? Or why this does indeed measure this. But before we go on, I just want to point out, we are now starting to think about how our curve or how our surface curves in space. So we're starting to get back into this familiar territory, and you can imagine that curvature will be playing a role here very shortly. All right, so first of all, the second fundamental form turns out to be a quadratic form, which means that if I plug in a value v or a vector v, with each of its components, v1, v2, then the outcome, the outgoing expression, is an expression that involves v1 squared, v2 squared, and v1 times v2, right? So it's going to be a quadratic form. And I'll simply say as a fact, right, maybe a linear algebra fact, but we can assume that this is true, that the second fundamental form can be written in matrix notation. Specifically, if I want to plug in a vector v to the second fundamental form, that can be written as v transpose times m times v for an appropriate matrix M. And because our tangent space is a tangent plane, two-dimensional, then our matrix should be a 2x2 matrix. And the entries, we'll denote these as L11, this is a capital L, L11, L12, L21, and L22. Our goal for the short term, for the rest of this video, is to try to find a nice way to write the entries Lij. So what are the entries of this appropriate matrix? Oh, my bad. Let's get that to the right spot. Okay, so let's take our vector v that we want to plug in, and because we are working in the tangent plane, I want to represent it appropriately according to our typical tangent plane basis, specifically represented in terms of the vectors x sub u and x sub v. All right, so let vector v represent, or let it be the vector a x sub u plus b x sub v, and let me represent that in its column form as ab. So we remember, again, that the ab here doesn't mean ai plus bj, it means a x sub u plus b x sub v. Then that means that our matrix, or I should say our second fundamental form, in its matrix form, will be written like this. And then once we compute the multiplication and we go through all of this, we'll end up with the following expression, right? We'll have a squared L11 plus ab L12 plus ba L21 plus b squared L22. So our goal is to figure out what each of these Lij's are. And to do that, let's try to compute the second fundamental form in its longhand way, right? So not in its matrix form, but by taking the definition of the second fundamental form as the dot product negative d n sub p of v dotted with v. And so if I do that, and I write my vector v in this form up here, right, axu plus bxv, axu dot bxv, then I can apply the differential to this first term, right? And again, the differential of x sub u will be n sub u. The differential of x sub v will be n sub v. And then the differential will be linear, so I will get this expression dotted with axu plus bxv. That won't change. So I'll apply the differential. I'll get this line. And then I'll just distribute this. And what I'll get is a squared nu dot xu plus ab nu dot xv plus ba nv dot xu plus b squared nv dot xv. So we end up with this expression down here, all with a big negative sign out front, I should say. And then if we compare our two answers here, it becomes really, really apparent what our entries, the Lij's, should be, right? Each Lij up here has a corresponding term down here with that negative sign attached. And so, once we make that observation, we realize that we can write our matrix as dot products of our vectors xu and xv with our normal derivatives nu and nv. And the result is as follows. The second fundamental form can be expressed using these negative vectors. L11 is negative nu dot xu, L12 is negative nu xv, L21 is negative nv xu, and L22 is negative nv xv. I'll point out that we can also write it in this form, right? And to see this, right, to really see this, I'm going to just look at this first entry here. Oh, whoops. I want to look at, this first entry and show that those two entries are actually equal to each other. And to do that, what I'm going to do is a similar trick to what we did before. I'm going to make note of the fact that, nu, n, just n by itself, dotted with xu is equal to 0. And so I can take the derivative, right, the u derivative in this case, of both sides of this equation. And so the u derivative of 0 is just 0. The partial u derivative of this side is nu dot xu plus n dot xuu, right? So there's that dot product rule that's occurring here. The u derivative will hit each of these terms separately, and we'll get a product rule. So if nu dot xu plus n dot xuu equals 0, then I can just move this piece here to the other side of the equation, right? We can subtract. I should say to do that, we have to subtract, and then the end result is just exactly this. So I can replace the negative nu xu with a positive n dot xuu, and that's true for all four of these as well. All right, so this is our matrix form of the second fundamental form, right? It requires taking two derivatives of our parameterization and then dotting it with the normal vector, or alternatively, taking one derivative of our normal vector, one derivative of our parameterization, and then taking those dot products there as well. The final thing I'll say is that similarly to how, let's get rid of all that, similarly to how our first fundamental form had differing notations, right? It used this letter G, but it also used the capital letters E, F, and G. I just want to point out that our second fundamental form also uses different letters. So we have some notation. The notation that our book tends to use is L11, L12, L21, L22. But we also have the notation of lowercase e, lowercase f, and lowercase g, in case that's not confusing enough for all of you. So we typically won't use that notation. We'll typically use this notation, but I wanted to mention that. So this is our second fundamental form, and much like the first fundamental form, this will be fundamental to proving different or computing different quantities about our surface.